Hey everyone, welcome back to part 2 of our video lesson on section 2.1, which is called Rates of Change and Limits. So far, we've had a long discussion on limits, and you may be happy to know that this second video where we discuss the rates of change part of this section, it's not as long. I'm going to jump back into my slides here. I think I need to go to slide 21. What's 9 plus 10? 21. Sorry. Okay, here we are. And I want to say before we begin that this might seem a little bit randomly placed. We had a really long discussion, as I said, on what a limit is and how to evaluate a limit, and then all of a sudden we're talking about average speed, and we'll eventually move on to other rates of change. And that might feel a little bit weird. What does a limit have to do with that? Well, you're going to see as we go. Average speed and then finding instantaneous speed, those are foundational concepts to beginning calculus. And so in the very first section of the very first unit of the year, we start to build that foundational knowledge. And what you're going to see as we keep going, like you're not actually going to see me write out a limit today. But finding instantaneous speed is defined by a limit, and you're going to see it in a very basic form today, a numerical approximation way, we could say. And then we will build that up to a limit definition, which will then build up to something that's hugely important to calculus, and that is a derivative. Okay. So I just wanted to note that that's where we're going with all of this, and that's why this is in the first section. Okay, so what we have here is a very basic definition of average speed, or a little formula, whatever you want to call it. Average speed is the distance covered divided by elapsed time. And I came up with a very simple example to start. When I'm driving on the Pennsylvania Turnpike, I actually do this, it's a little bit embarrassing, but I often calculate my average speed as I go. Meaning I think about what time I was at a starting point, and I think about what time I was at an ending point, and then I do my little calculation to get my average speed. I don't know why I do that, it's just, I guess maybe I get bored. So I do math in my head. So here's an example of me doing that. Let's say I start at mile marker 57, which is Monroeville, at 5 o'clock, 5 p.m. let's say. I should probably have that there, 5 p.m. And I end at the Donegal exit, which is near where I live, and that is at 5:30 p.m. Okay, so a half hour it would take me. My question is, what is my average speed? Okay. So I'm going to find the average speed, and I want to note to you that the way I'm going to set it up, you might look at it and say, she just did a whole lot more work than she needed to do to answer this question. But I promise you there's a reason that I'm showing all of this work. I mean, without giving away too much, I'm showing all of the work that I'm going to do because it will set us up to be successful as we move on through more complicated problems. But yeah, that's why. Okay, so what I'm going to do over here is I'm going to write this as an ordered pair. At 5 p.m., I'm going to call that a time of 0. And that'll be the x-coordinate of my ordered pair. And the y-coordinate will be the mile marker, so I'm at mile 57. At 5:30 p.m., I'm going to call that a time of a half. Does that make sense? Okay, think about this. I want to calculate my average speed in miles per hour. That just is something that makes sense to a lot of us, right? So rather than keeping this in minutes, if 5 p.m. is a time of 0, 5:30 p.m. is a time of 30 if we're in minutes. However, I want to turn it into hours, so I'm going to change that to a half. And that'll be my x-coordinate or my t-coordinate, whatever you want to call it, of the second order pair, and the mile marker, which is 91, is the y-coordinate. Okay, and then if I'm doing average speed, take a look up here. Distance covered. Okay, distance covered would be how far did you go if you started at 57 and ended at 91. Well, one way that you could show that is you could write that as 91 minus 57, right? Does that make sense? over elapsed time. How long did it take you? Well, obviously it took us a half of an hour, but I'm also going to write that out as a difference. I'm going to write a half, which is where my ending time, minus 0, my starting time. And the reason I'm writing it out like this is because I'm hoping that you recognize this. What is this? Where else in algebra? Okay, you probably saw it beat to death in Algebra 1. What is this? A difference in a numerator and a difference in a denominator, a quotient of differences. That's called slope, right? y2 minus y1 over x2 minus x1. That's what you're doing here. Okay, let's finish the calculations. 91 minus 57. This is the hardest part. Mental math. What's that, 34? Yeah. And a half minus 0 is a half. 34 divided by a half is 68. And that would be my average speed in miles per hour. 68 miles per hour. Keep in mind we're on the turnpike, so don't be like, whoa, she drives so fast. It's turnpike. Okay. Now, the most important thing I want you to get out of all of this is that if you're doing an average speed, that is finding the slope between 2 points. Starting point, ending point. You can set up ordered pairs and you can find the slope between those 2 points, and that will get you your average speed. Let's apply that idea to example 8. Again, this is one where you might think that I'm doing more work than is necessary to answer this question, but it's kind of important that you set it up like this. At least I think it's important as your teacher that you set it up like this so that you can then take this really simple concept and apply it to something that's much more complicated. Okay, here we have a rock breaks loose from the top of a tall cliff. What is the average speed during the first 2 seconds of fall? We need this equation, by the way, in the note. Experiments show that a dense solid object dropped from rest to fall freely near the surface of the earth will fall y equals 16 t squared feet in the first t seconds. That's basically like 1/2 at squared if you're familiar with physics formulas. Half times 32 for gravity in feet per second squared times time squared. All right, anyway. We're asked to find the average speed over the first 2 seconds of fall, and so I'm going to set that up first as a time interval. First 2 seconds of fall would be like saying, let's start at time 0 and go to time t equals 2. Okay, so this is an interval of time. We can then take that interval of time and we can turn it into 2 ordered pairs where the time value is the first coordinate in each ordered pair. Okay, we will get the y coordinates from the formula that I circled. Y equals 16t squared. Let's sub 0 in for t. 16 times 0 squared is 0, so we're starting at a height of 0. The next one would be 16 times 2 squared. That'll get us our y coordinate right there. And what's that? 2 squared is 4. 16 times 4 is 64. Make sure you do the order of operations correctly. All right, so yet again, I now have 2 ordered pairs, and if I'm asked to find the average speed, I can just show that as the, ooh, my handwriting is so bad still on here. I'm trying. Okay, that's the slope between the 2 points. So I'm going to take my y2 value, my ending, minus my y1 over x2 minus x1, and get an average speed of 32 feet per second. Okay, so again, a fairly easy and quick problem where I maybe made it more complicated than it needed to be, but I did it for a reason. Okay, I did it for your benefit. Finally, let's take a look at example 9. This is where my students think, oh my gosh, we're almost done. Awesome. No, okay. Example 9 is where the real work in this last little bit of section 2.1 comes in. Find the speed of the rock in example 1 at the instant t equals 2. Okay, so we are now trying to find something called instantaneous speed or an instantaneous rate of change. And that is much more complicated to do. That's what we're going to need to build up to all throughout this chapter and the beginning of the next chapter, the next unit of the course, to eventually call it a derivative. Okay, so this is a really like clutch concept right here, where you're going to see it today in this video in a really super inefficient form, meaning it's going to take a lot more work than it should. And you're going to see it in pretty basic math terms, meaning we're not going to do a ton of real calculus. And we do that because you need to build up the foundation of understanding what it is you're doing before you see the calculus that leads into it. However, okay. Sorry, I just got distracted by something. Okay, so what I'm going to do is I'm going to try to set this up really similarly to how I just set up example 8 to show the similarities, and then I'll show you the main difference in what you need to do. Okay, so I am now trying to find the speed at the instant t equals 2. I could still try to set that up as an interval of time. However, if it's at an instant of time, the beginning time and the ending time are the same. So my interval is going to be set up as from t equals 2 to t equals 2. Okay, then I'm going to try to just do the same thing that I did for the last example. I have two ordered pairs. I already know that when t equals 2, the y-coordinate is 64, so I'll just write that in here. And if I'm trying to find an average speed, then I would try to find the slope between those 2 points. And now that that's written out, I hope you notice what has just happened. What we are getting here is 0 over 0, which you should recognize from the first part of this lesson as an indeterminate form. Now, what that means is there is an answer to this. We should be able to get the answer, but we can't get it just by straight subbing in these points to our slope formula. So we need to begin to think about finding this answer as a limit. Okay, now I told you I'm not actually going to write out a limit for today. However, what I am going to do is try to sort of numerically approximate the limit with various other intervals, time intervals. Okay, let me show you what I mean. So I'm going to set up a new time interval. However, I know I can't go from 2 to 2. It doesn't work. We just tried it right there, right? So I'm going to say, well, can I set up something that would be close to that time interval, 2 to 2? You know, could I use something else that's similar? Yeah, right? We could use, instead of the starting point being 2, could we not use a starting point of like 1.9? Or even if you want to say, well, I want to be pretty close, 1.99 to 2? You know, that would work, right? Let's see what happens. So we're going to set up two ordered pairs again. I already know this ordered pair is 2, 64. This ordered pair, I'm just going to write it as 1.99 comma some y-coordinate, which I would find by, just a reminder here from the first part, your y comes from the equation 16t squared, y equals 16t squared. So I'm just going to write it like that, 16 times the quantity 1.99 squared. Instead of doing rounding in there, let's just write it like that. And, you know, I should be able to find the slope between those 2 points and not get an indeterminate form. Hopefully, right? Okay, so I guess before I grab my calculator, I will write it out. My y2 is 64 minus my y1, I just wrote it as, whoops, I bumped a button. Which changes all of my settings on my pen. Thank you, technology. Okay, 16 times 1.99 squared for my first y-coordinate over 2 minus 1.99. Now, this is where my writing starts to get horrible because I have to write so much. Now I'll go to my calculator. just let the calculator do that work. All right, just to have as least amount of typing as possible, or least amount of steps, I guess, as possible, I'm going to group the numerator with a set of parentheses around it, and what's that? That's 0.01 in the denominator, right? We can do that mentally. 2 minus 1.99, 0.01. Okay, so here we get a slope or a speed of 63.84. Oh, I bumped the button again. Okay. Okay, my computer just went completely crazy, but I fixed it, and here's the answer that we were looking for. So just to recap, going from time interval t of 1.99 to t equals 2, we found the slope to be 63.84 feet per second. Now, you shouldn't take that exact answer as your answer to the instantaneous speed at t equals 2. That was just something that's really close to your answer. This is why I said that this method is really super inefficient. You should do this sort of thing where you approximate a speed that's close to the speed that you're finding more than one time to get a solid answer. So, you know, we said let's choose 1.99 because that's close to a starting point of 2. We could get even closer with a starting point of 1.999, right? And this is usually where in class I have my students groan and say, "Are you kidding me? Like, what?" And then I tell them, "Oh, there's more. That's actually only approaching from one side, meaning having an earlier start time. We could also approach from the other side and say, let's make our starting point 2, and we know we can't make our ending point 2 because that resulted in the 0 over 0, but we could make our ending point something like 2.01, right? And we could find the slope between these 2 points. We could say start at 2, and we could get even closer to an ending point of 2 by making it 2.001. And this is the idea of a limit. You can't get exactly to an interval of 2 to 2, but you can get close to it, and most importantly, you can get close to it from both sides. So I don't want you only approximating from one point. You need to approximate from both sides to see that they're coming to the same value. Okay, now I'm not going to make you suffer through watching me do all of this 3 more times, but I do have it summarized here on the next slide in a nice little table that I think you'll see approaching from both sides you get to value. Okay, so here in the first row we have the interval that we did together from 1.99 to 2. We set up those 2 ordered pairs. Whoops, there's a parenthesis missing there. It's like missing everywhere. Oh, goodness gracious. I have to fix that. I'll put those parentheses in as I talk. Okay, there should be a parenthesis here, here. Okay, so we found that speed to be 63.84. If you would change the starting point to 1.999 to 2, you can see the difference in our first ordered pair, and you can see a slightly higher speed of 63.98. If you change the ending point instead of the starting point, so here we're starting at 2, but we're going to 2.001, or really maybe we'd say let's start at 2.01 and then move to this one, 2.001. I wanted to show them sort of in a progression of approaching. That's why they're in this way. You can see that you get slightly higher speeds, 64.016 and 64.16. Okay, the interval, the speed of the interval that we were trying to find, which remember was 2 to 2, that would fall right into here, okay, right in between these. And, you know, you could say, well, what is my speed really close to for each of these calculations? It's close to 64. And so that is what we are going to take as our answer to example 9. What is the instantaneous speed when time is 2, or what is the speed at the instant t equals 2? It is 64 feet per second. Now, once again, I just went over that example in a way that's very inefficient. It took a lot of calculation, it took a lot of explanation, but it's pretty basic math, and that's why we start there. Set up an interval that you can do, use ordered pairs that you can find the slope between, and get those answers and approximate your instantaneous speed from those answers. Okay, as I said, eventually what you're going to see this as is a limit. Okay, we'll talk about that very soon. And then in the next unit, you'll start to see this being called a derivative. Okay, so super exciting stuff coming up. Can't wait. I hope this video was helpful as usual. Bye.